Hello. This is going to be a talk on it's an introduction to binary exploitation. So we're going to be going over very basic binary exploitation things. So basically covering buffer overflows, overwriting data on the stack, and then let me put Slack. Overwriting data on the stack, and then overwriting like return address and all that fun stuff. So if you're like experienced, like it's gonna be like the very basics. So if you're experienced, you probably don't need this talk. But if you're new, um, then yeah, this would be helpful for you. So what is binary exploitation? Basically, it is. Hold on. All right. Basically, so it's like using bugs in a like compiled program, so written in like C or C++ or I don't know, Go or Rust or whatever new fancy languages are being developed now that compile to machine code. Using bugs in those programs to gain like control um of the program itself and to like be able to like execute like arbitrary commands. So your general goal is to get like shell access. So like this kind of shell, like terminal shell. So you can type in like whatever fancy commands you want. Um, so like real world applications would be to like jailbreak or root your phone, or even the like Super Mario World credits warp is a example of binary exploitation. So it's a pretty cool topic, pretty important. Um, and so there's like there's software everywhere, right? Your favorite library that you use, like your favorite like C++ library or something. Um, there might be a bug in there that allows for popping a shell right through binary exploitation, and so as like ethical hackers, you're like what you can do is find these bugs and then report them to like companies like Uber and get $10,000 or more, or less. I don't know. It depends on how much they want to pay you, but yeah, you can get some money out of it. And um, a lot of RPI-sec people, their career, like a big part of their job is doing binary exploitation. Um, Yeah, so some very like basic but very important things that we need to keep in mind when doing this kind of stuff is that computers just act on memory, right? So they just act on bytes in memory. So basically everything on your computer is just made out of bytes. I don't care how pretty your desktop wallpaper is, it's just bytes to your computer, right? And so it'll do things like it'll do whatever the bytes tell it to do, basically, right? So when you compile your program, that is just turned into bytes. When you run your program, your computer it like interprets those bytes and does different things based on what those bytes say. So the important thing with that is that it doesn't know right from wrong, right? It doesn't know if the stuff in like the like program's bytes are correct or not, right? You can just make a program that'll just crash immediately, and then it'll just crash happily, right? So our goal as attackers is to find bugs in the program that can allow us to kind of like change what the program does, make it do things that the programmer did not really expect it to do. And so the way we do that, C is a very low level language. Most of these binary exploitation, like CTF challenges, also called pwn challenges, um, are written in C, some in C++, and I guess some like newer CTFs are doing like Go and Rust or something. But Yeah, basically, the common thing with all those languages is that they all compile to machine code. Um, and C itself, it doesn't really do any like memory sanity checking. So, um, if you overflow a buffer, it won't care. It'll just keep running until it can't anymore, or until it finishes the program, right? Um, and so that means that it's very easy to kind of just make mistakes as a programmer, right? I'm sure in your like data structures homeworks, you've all encountered seg faults, which when you're programming is not fun, but when you're attacking, it's very fun. When you get a seg fault, that means that you're doing something right as an attacker. So with that out of the way, let's start breaking stuff. So we're going to be going over these challenges from our like internal practice CTF thing. Any RPI student can access it. Here's the URL: fairgame.rpis.ec. Just make an account, sign in, and then you can download the challenges. So we're going to be looking at the PON category. It should be on the bottom of the page. The first two challenges from that. So okay, I'm going to open up the Fair Game PON 100. So I'm going to open up the source code. You can download both the source code and the compiled executable. So here we can see it's a very simple program. These comments are not there originally, but I just added them. So basically it puts like these like values on the stack, right? So what that means is, because an int is 4 bytes, right? That's how they're represented in the computer. Every int takes up 4 bytes of space. And then this, as a C programmer, you'd kind of think of this as a string, right? Okay, I'm making a string that can take 20 bytes of characters, right? But really, it's just 20 bytes of space that's allocated for the program to use as a string. So essentially, we are allocating 24 bytes. 20 plus 4 equals 24 bytes on the stack. And then we are printing, so the program is printing, please enter your name. We can do that with this gets command, with this gets function. And then it'll check this points variable, which is set to 0 initially. It'll check the points variable. If it's equal to this magic value, 1337 dude in hexadecimal, it'll pop shell, right? So binsh is the system's shell. So then this is what your end goal is, right? Is to gain shell access on the computer that's running the program. And if it fails that check, if points is not equal to this value, then it'll just print this sad face and exit. So actually, okay, I'll keep this open. So we're going to be focusing on the stack a lot in this talk. And one of the most important things about the stack is that there's this concept of a stack frame. So whenever a function in C is called, and then this includes main, the program, it puts a stack frame on the stack, which contains these three things. It contains space for the local variables. So in our case, that'd be the 24 bytes here. So then this would be like the beginning of the stack frame for that function. A base pointer, which is stored in, which would be the, so the base pointer would be stored in the EBP or RVP registers, and that's a pointer to the previous stack frame. So which this allows for like stack walking. So then you can view um, like local variables, like the values of those in previous functions. And also the return address at the end of the stack frame. So it's in that order, as you can see here. And so here in the green is our foo buffer, the 20 byte buffer. Then the points int. This is so then this takes up 4 bytes of space, and then the base pointer. Because pwn 100 is a 32-bit program, pointers take up 4 bytes of space as well. So this is 4 bytes, and then this is 4 bytes. And so again, gets, it'll just read input from standard in. So it'll just read user input. So I can demo that here. Just start a new thingy. Oops. There we go. So let's keep the source code open on the side, then I'll use the left for running the program to demonstrate things. Rewards program. So here we can type in a name, then it'll say welcome name, ASDF. And yeah, so it uses gets to kind of get this string from the user. And so we can fill it up. We can fill up the foo buffer, the foo like string with a bunch of stuff, right? In this case, hex 41 is just a bunch of A's, so 20 A's. And so the gets function is like really, really bad. If you look at the man page for gets, you'll see here in the bugs, never use gets, because it's impossible to know in advance how many characters gets is going to read, which means that the user can just send like a whole bunch of bytes, more than your program is designed to handle, and then that can overwrite things in the stack, which can make the program just stop running. It'll segfault, or it'll just make it do malicious things in our case. And so here in the description, it says it reads a line from standard in until a new line or end of file. And again, no buffer overrun is performed, or no buffer overrun check is performed. So you can pass in a pointer, in our case, foo. The pointer will point to some piece of data, right? So in our case, it'll point to foo. But really, you can pass in any pointer, and then it'll just put the bytes that it reads at the pointer. But yeah, basically, don't ever use it. This is another function, scanf, that has a similar effect, as we'll see in pwn 200. So if we pass in, let's say more than 20 bytes, if you pass in 50 bytes, right? Oops, a times 50 into our program. What just happened? Okay. Okay, into our program, then it segfaults, as you can see here. So we did something bad. So what happened was because gets, it'll just keep reading bytes, as many as the user can send it. So we sent 50 bytes. The program's only designed to handle 20 in that gets call, right? So what happened was that we went past the end of the space allocated for foo, and then we overwrote data past that. So if we just put in 21 A's, then we would overwrite the points, the value of points, right? Because points is right after foo in the stack. So the 21st A basically goes to foo, and then changes the value of foo to hex 41. And so that's kind of how you solve the challenge, right? At the end, after the gets call, the program compares the value of points to 1337 dude. So our goal is to overwrite the value of points with that. And yeah, so little quick note with Endianness. So my machine and yours too probably uses an x86 architecture, which represents data using little Endian. So what this means for us is that numbers would be backwards. So this hex 01, 02, 03, 04 would become 04, 03, 02, 01. So which means that we have to put in our magic value 1237 dude in that order. So you can see that here, this is kind of backwards, right? It takes the last byte of this number, the 0D, and puts it at the first thing in the input to the program. So if we do this, we have 20 plus x0d, xd0, x37, x13, and then pass that into the program. It'll say we did it because we did do it. We changed the value of points to 1337 dude, which is kind of cool. So what we just did there with the Python and then this pipe is so the pipe, it redirects the output from this first command and makes it the input for the second command. So basically we took all the A's that are printed with this Python. You can see here the A's, and then the 1337 dude. You can't really see that in here because those aren't really like printable human readable characters. So it tries to print it and it prints like a 7 here and then kind of messes up over here, right? But basically it takes all of that data and then passes it into the rewards program executable. And you'll notice that here this is supposed to call bin.sh, right? It's supposed to give us a shell, and shells are supposed to let us type in like cool commands like ls, right? But I'm not doing that in the shell spawned by the program. I'm doing that in my own shell, and that's because the program just exits immediately. And the reason for that is because standard in, it closes basically. After this Python thing exits, it just closes. So it'll send this string, these A's, and then the 1237 dude, and only that. So in order to have it stay open so that we can actually interact with it and like type cool commands like ls, where am I? Here? Yeah. We need to chain another command called cat. And so now we can type in cool things like ls, and you can see here we are in the internal shell. So we typed in ls, and then it gave us the expected output of ls. And so what cat does is, if you just type cat, it'll wait for input, and then it'll spit it back at us when we give it input. And so why this is important is because standard in stays open, right? Cat will not exit until you tell it to. So until you give it end of file, or until you type Control C or something like that, right? Until you stop it by yourself. So our issue with earlier, where the program would exit by itself, is fixed by chaining the Python call with a call to cat afterwards. And so here's basically what happens when we do that. Here, this is the Python one, right? So Python and then our executable name. So it'll redirect the standard out for Python into the standard in for the executable. Here, it will do the same thing. It'll do the Python thing in blue and then the executable in green, right? So it'll redirect the output for Python into the the executable, but then it will go on to cat. It'll redirect the centered in, the input for cat, into the output for the executable, or into the input for the executable. But because cat stays open, it'll not close, which allows us to type in commands into the shell. And so you can see it just goes from this one to this one. And so let's take a look at what that does to the memory in a debugger. The debugger would allow us to examine like the stack, the state of like all the registers, which will help illustrate the point of what we just did. Now this is wrong. This should be we're going to be using Jeff, not Peta, for this talk. But so if I open the program in GDB, so the first thing that we want to do is disassemble main so that we can see the assembly code that makes up this main function. So this corresponds to this, all this stuff here. And so here you can see the comparison of something to 1237 dude. So this this comparison is this line of C code basically, which means that this EBP minus 0xc is where the program looks for the value of points. So let's put a breakpoint after or right before the program calls gets, right? Because that way we can see what our input does to the program exactly, in like a step-by-step manner. So we're going to be doing this fancy thing with GDB, which basically allows us to do what we just did earlier, where we redirect the output of this Python call to the input for the program within GDB. So this is just some fancy syntax. Let's put 20 A's. So we send 20 A's into the program. Oh, I forgot to put a breakpoint. Hold on. Here you go. Now we do that. So now we're right before gets. When we go to next instruction, which will just make it go down the thing. So we can see if we examine our stack, we are on the instruction after gets. So let's examine 20 words from the stack pointer. So you can see everything here is kind of normal, right? There's no 414141s. Yeah. But if we put more than 20, let's put like 30. And we do that. Hold on. Let's see. Okay. Yeah, so then if we just keep going through the program, then it'll just exit normally. If you put like a bunch, like 60 or something A's, so way more than 20. Where are my A's going? This is kind of weird. Okay. Let's see. I guess let's try again. I don't know. Yeah, sorry for the technical difficulties. I'm not really sure why this isn't working. Okay. Sure. Okay, yeah. Guess that works now. Okay, so let's put another breakpoint. Sorry about that. I guess like the redirection from Python to GDB or messed up or something. So let's put a breakpoint again at main, at the call to main, and then oh yeah, what this Python-C does, by the way, is it just allows us to pass in some Python code, and then it'll just run that automatically. So then we don't have to, like normally when you type Python, it'll wait for us to kind of type in something. But with the -C, we don't have to do that. It'll just take the input and run it automatically. So we're about to call gets. Let's go to right after we call gets, and now you can see our stack pointer is A's now, right? We got some A's. So 414141, which means that let's go back here. Which means that we went past the end of foo. We went way past. We put in a bunch of A's. So we overwrote some stuff that we weren't supposed to on the stack, basically. So let's do a normal amount, 20, and then do that. Yeah. So now you can see the A's are there now. I'm really not sure why they weren't earlier, but so let's examine the stack pointer. You can see here is our A's, the 414141s, and there's 20 of them, right? There's 5 groups of 4. So then after that, these zeros are for points. Again, let's go back here. As you can see here, there's because points is set to 0 initially, right? So these zeros are for points. This thing is the base pointer, and then this is the return address. But so what happens when we type in our address as well? So let's do, or our number as well, rather. So let's do that. D0 3713. So this is 1237 dude and little Endian again. What the heck? Oh, I forgot to. Okay, there we go. And now let's examine the stack again. So now we can see. Oh wait. That's interesting. Okay, yeah. So now we can see we have like this 37. There's a 90 here for some reason, but yeah. So I guess we went past one too far, but so we have our 13 and then 37. Then there's an OD there. I'm not sure why that's messed up, but let's try 19. Is the redirection messing up again? Let's see. Let's set our breakpoint again. No, let's do that. Should be 20. Okay, interesting. See what happens if you go to the end of the program. Okay. Yeah, it exit normally. I guess it's supposed to, but did I type this wrong? Wait. Zero D. Yeah, so let's see. Let me compare my input with this. I might have typed it wrong. 0D D03713. Okay, interesting. Oh well. I think you probably get the point though. Like, basically we were able to read past what was expected, read past the 20 characters, and kind of put that extra data later on the stack after the foo buffer. So, yeah, you can here you can try it for yourself. Here's some like basic GDB commands. So what I did so far was disassemble main. I put a breakpoint on the guts call, and then I used ni, which is just like when I keep like going down the assembly, it's just typing ni basically, which is next instruction, and then this allows you to pipe into GDB, which I guess isn't working for me for some reason, but yeah. And so here's like the solution as we saw in the command line. So that was a very like ideal program where it has this magic value that it compares to this magic number, right? It compares points to this number, and then it calls shell. But we don't always have this magic variable that we can just overwrite. So a more general solution would be to overwrite the return address. And so these are three questions that we're going to get into right now, basically. So if we corrupt past points, then we can do a lot more powerful things. And more generally, when a program segfaults, like we're gonna see what causes that. So here's another program. Again, it's a pretty simple program, but there is a nested function call, or like there is a call to func in main. So after func does its things, after it prints hello world, how does it know how to get back to main? So it does that by putting a return address, which is basically an address to the next assembly instruction onto the stack. So here we have the call to func in assembly. Yeah, so here the call func, and then the address after that, this hex 40051F, we can find that here. So this is before the call, this is after the call. We can look at the stack, and there it is, the 40051F. So what happens after, or when a function returns, is it pops everything off of the stack frame, basically. So it'll pop the return address into the instruction pointer, into the EIP or RIP register. And then that's how it basically continues execution of the function that calls that the function that it just returned from. So in our case, that's how it knows to continue execution after func returns. So the return address in this case would just be whatever the assembly representation of this is. It'd be the address to it'd be the location of that instruction, which is the 451F. Yeah, so as I just mentioned, it pops the return address into the instruction pointer. And so what if we change the instruction pointer? We can do a lot more powerful things. So let's look at pwn 200. 200, and then so I'm going to do the same thing. Open the source code on the right. Then I can have GDB and the program execution on the left. So I'll just clear this. Oops. So this is a very similar program. It's even shorter, but so again, we have this foo buffer, which is 64 bytes long. And this fscanf, which basically this will read from standard in. So it'll read input from the user. It'll read a string from the user, and then it'll put that string into foo. And then it'll, oh, there should be 0. And then it'll exit. It'll print hello whoever. So I guess in this case name, right? Hello John, and then it'll just return 0. But there is this win function, right? It's never called, but we can change that. We can call it. And we do that by overwriting the return address. Yeah, so here, this is an example of when we put like 40 A's in the previous one into the buffer that only takes 20, we went way past the return address, but we did overwrite the return address with A's. And because basically when the program is executing, it'll just do whatever instruction the instruction pointer is pointing at. But since 414141 doesn't point to an actual instruction, then it doesn't know what to do. So that's what happens when a program segfaults. And the reason why that's good for attackers is because a segfault means that we've made the program do something that it's not meant to do. AKA, we've put data that's not supposed to be in the instruction pointer, but we, made it, like we put it there anyways. Which means that we gained control of the program's execution. Yeah, so let's do a demo of this function, or of this program, control flow inc. So the first thing that we want to do is we see this win function, and we need the address of it in order to, actually let's do that. Okay. So we have this this win function that we want to jump to, right? So we need to overwrite the return address of main with the address of this win function. So we can find the address of win by printing win. We can also print main if we wanted to, but there isn't really any use in that. But just to demonstrate the point, this print thing will just print like whatever number this symbol corresponds to. So in this case, it'll print the address of win, which we have here. So if we disassemble main, and let's break on the function where it reads input from the user again. So break right here. Actually, I'm going to copy this. And just put it there, just so that we can reference it. But yeah, so let's put a breakpoint over here. Then let's do our A's again. Well, let's put in 64 A's. And so we're right on the call for fscanf. Let's go one instruction after. So it's returned from fscanf, right? When it calls fscanf, it does the same return address thing that we just discussed earlier. This was the return address for the stack frame that fscanf had. So now we can see all our A's on the stack. Let's examine it. Let's examine 40 words this time on the stack. And so we can see we have a bunch of A's. Goes all the way here. Then we have, this is probably the base pointer and then the return address. So if you look at the stack diagram, again, there's just, oh, this is the wrong one. Okay, but yeah, so let's pretend that this points thing isn't here because that's not in this program. But this is the same, right? Where this is 64 bytes, and then there's the base pointer, and then the return address, which means that we can fill up the foo buffer, but if we only fill this up, then we're not going to do anything, right? So we need to put 64 to go past the base pointer. So we need to change the base pointer so that we can change the return address. So let's put 68 A's now. And then, oh, you can see cannot disassemble from PC. Oh. But yeah, so now our A's are here, where they used to end here. And now this is the return address, so let's run it one more time, but let's also pass in the return address. So xb6 hex 91 hex 04 hex 08. Oh geez, what was that? Let's try that one more time. Break and then do that. Alrighty, it really does not like that. Let's try that with. Interesting. Oh wait, okay, hold on. I recompiled the program, so I think that might have messed up some of the addresses, but let me just re-download it just to make sure that nothing else was changed in the process of me recompiling it. My bad. Okay, now let's run it one more time. Let's see, disassemble main, and then put a breakpoint on the fscanf here. Then do a run. Oh, oops. I have to make the program executable. /control inc. Okay. Now let's do the run thing again. Or let's print win. Yeah, the address did change. Okay, 4B 850408. There we go. Okay. Now we have our A's. So now let's look at the stack again. Hold on, I might have typed in the address wrong again. $804. I guess not. Okay. But yeah, so if you look at our stack, we have why is this out of order? But yeah, so we did put some data here. That's not supposed to be there, right? This is, I guess it's kind of scrambled. I'm not sure why, but you know, like this should be our address. And so if we do the same Python command in outside of GDB, I guess it kind of messes up there for some reason on my setup. But let's do our A's 68 plus hex 08 hex what was it? X0 4B 850408, and then there. Let me pipe that into the program. Oh, sec vaults. Okay. Let's see. Right. Let's try that with cat maybe. Okay. Let's. What is going on? Let's see. So Okay, let's do the breakpoint again. Says main. That lines up with that still. Okay, cool. And let's do this redirection. Okay, so my A's are there. What we can do is we can so again, if we look at the stack diagram, here we have the base pointer, which is 4 bytes. So what's in EBP is the start of it. So to get to the return address, we just need EBP plus 4, basically. So if we print that, we can see that that is still intact. It's interesting. Give me 1 second. Oh, you know what? That's why. Okay, I'm not doing Python 2. So, yeah, okay. I did it. Okay, cool. Thank God. So, what was happening was between Python 2 and Python 3. So, like in Python 3, they changed up how they interpret or how they like print raw bytes, I guess. So, it was printing like I'm pretty sure just this as like normal string. So it was trying to pass that as like normal string into the program instead of the raw bytes. So that's completely my bad. But I bet if we go back into GDB, do our breakpoint again, do this and change this to Python 2, then look at that. That's our address. Okay, so right after our A's, we have the return address. And then when we return, you see instead of going, or so it returns from main into the win function, so which means that we did it correctly. Yeah. And so again, if we do that here in the shell, then we pop shell. So we call this function, we see the printf you did it, we did do it. Took a lot longer than it should have because I forgot the Python thing, but yeah, you got the gist of it. And that EBP plus 4 or plus 8 for 64-bit executables is a very useful thing. What I was going to do was calculate the distance from the start of the buffer, which is pointed to by wait a second. Okay, so if we disassemble main, we can see in fscanf. Let's see. Yeah. So here, when it calls printf, right, it puts this hold on. So it puts EAX onto the stack, right? EAX points to our buffer. If we examine EAX, it says A 68 times, right? We put 68 A's plus some extra stuff, which is this, plus some extra like non-printable bytes. But so EAX prints to the beginning of our buffer, and which means that here, if we look in the Jeff stack state display thingy, what we can do is we can do print EBP plus 4 minus that. Let's print that as numbers 68, right? So when my Python thing was messing up, when I was still using Python 3, I thought that okay, there might have been something wrong with how I was, with how with how many A's I had, right? So I might not have lined up my address correctly. So you can use this to verify or to even just find out, right? Okay, the distance from the beginning of my buffer that I'm overflowing to the return address, which we can get, so the distance from the return address, sorry, this is EVP plus 4, which is the return address, to the beginning of the buffer is 68. And then we can just put in 68 A's. And then right after that, we can put in our whatever data we want. So in this case, the address of win. Yeah, that's should be it. Again, here's some very useful, very important commands in GDB. And yeah, here's the solution. So if you want more practice, which is really the only way to get better at security, I think, right? You can like read blogs and read papers and stuff like that, which does give you knowledge, but I find that in order to kind of master that knowledge, it's important for me to practice, which I kind of haven't been doing too much, as you can see with the Python 2 and 3 mistake, but you know. So here's some good resources. War Games is, I'm not sure if it's if people that aren't taking modern binary exploitation have access to it, but if you are, then you're already doing this. Here's some more public ones. So like War Games is set up by some RPI-Sec alum. And so I think you need an RPI email. I'm not sure if this is still the case, but you probably need an RPI email to access it. But it's like an online platform which is used in modern binary exploitation in the class, in that class, and it's very good. Very easy to use, very helpful. And so here's some other resources. Microcorruption, I haven't used it personally, but apparently it has a friendly user interface, so we all love those. And Pwnable KR is a classic. This is what most people recommend when they want to, or when someone asks like how to learn binary exploitation and even like reverse engineering. It also has some stuff on that. You go to pwnable.kr, register for an account, and then you can start doing the challenges on there. There's also Pwnable TW, which has some more like advanced, more esoteric techniques. So I definitely start with KR before going to TW. And yeah, play CTFs. If you go to ctftime.org, you can see upcoming events. There's one of them called Hack the Vote, hosted by RPI-Sec, you know, who seem like pretty cool guys. So yeah, we're hosting a CTF on the 23rd, on Friday. So you can play that if you want. I'm not sure if we're personally going to be playing it because we also set it up. So but yeah, you can definitely play that on your own. There might be some people in our RPI-Sec Slack who are also playing it, so you can probably form a little group. And yeah, if you need help with that CTF or literally anything else, you can come join us on our Slack, rpis.slack.com. And here's the website for Hack the Vote, our CTF. You can register on there and play and practice. Well, yeah, sorry for the technical hiccups. kind of embarrassing, but you know, whatever, it happens. Yeah, thanks for watching. Come say hi on our Slack.